Hello, my name's Jacob, and I'm going to be giving you a brief history of calculus. And at the end, I'm going to go ahead and teach you how to solve integrals using the U-sub method. So starting out in calculus, it was first really developed by humans in ancient Greece, so about 500 BCE. The ancient Greek Archimedes and Eudoxus, they used really early limit-based ideas in order to solve some issues that calculus will later on help us solve pretty complex mathematical ideas and equations. Archimedes first tried to calculate the areas under curves, so trying to find what this area is on a curve. And the method he would use to do that is very geometrical. So he would take shapes underneath these curves and find the areas of these shapes, because an area of a triangle is much easier than the area of a curve. And he would use other methods like that. Also use like simple spherical methods. So let's say you have a sphere you want to find the area of. It's easier to find the area of a square in that sphere than it is to find the area of the sphere itself, especially if you don't know um, the equations to find that sphere. And right now we have a bunch of area between the square and the sphere, and so if we were to just find the area of the square, it would be much smaller than the area of the sphere. So in order to kind of solve that, you can make smaller and smaller areas until you actually get um, a shape that's similar size to the sphere. So a five-sided pentagon, or you can go up to as many sides as you want. And the more sides that shape has, the less space there is between the shape of the shape you're using and the edges of the sphere. So the more and more you use, the more and more sides to that shape, more um, the closer you're going to get to the area of that sphere. So those are the ideas that the ancient Greeks were working with, and um, it kind of approaches some of the ideas of infinitesimal, like the infinitesimalness of calculus, and trying to find uh, the answer to a problem as it approaches even smaller and smaller segments. So ancient Greece was working with a lot of the ideas of modern calculus during this time. So next, moving on, is the Indian Islamic contributions, and those were done in about 5th to 14th century AD, so over 1,000 years after ancient Greece. The Indians and there Middle Indian and Islamic contributions to many of the ideas of calculus. So a really large uh, gap between those, and that's due to a lot of the collapse of the Roman Empire and the Dark Ages during that period. So there's not a whole lot of history between Greece and the next stages of human civilization. But luckily, in the 5th century, the Indians mathematicians started developing infinite series and kind of expanding on some of the ideas of Archimedes, um, kind of using more trigonometry in order to solve these ideas of the areas under a graph. In about the 12th century, Bhaskara II developed some ideas around derivatives in the context of planetary motion. So a lot of the ideas that the Indians were developing were kind of only a section total our total knowledge of how calculus works and interacts with other elements of mathematics. So they were developing very similar derivative contexts and trying to find instantaneous velocities. Another big contribution was by Madhava of Sangam Agrama, 14th century. He derived a bunch of infinite series of pi, sine, cosine. So a lot of contributions um, to our ideas of trigonometry and trying to find, I guess, developing these ideas that are pretty fundamental to how we talk about and think about calculus. So, kind of expanding on that, the infinitesimalness of calculus, and trying to find smaller and smaller areas until we actually get to the number we want. From Islam, running from about 8th to 15th century, a lot of development from scholars translating ancient Greek texts and other Indian texts into Arabic and thinking about all of these into different contexts and kind of developing this form of algebra that's foundational for calculus. So developing the ideas of using functions and developing algebraic notations in order to help us actually find out the answers to different algebraic equations in order to actually solve the things like integrals or derivatives, things of that nature. A lot of mathematicians looking into how to use motions of the Earth and the planets in order to help develop optics and other ways in order to study the nature of the world. Then a lot of that required some form of integration and trying to find the smallest numbers to get to where we need to get to. Another mathematician, Omar Khayyam, he explored more into the ideas of geometry and using cubic equations, and a lot of these ideas that he developed influenced a lot of the analytical thinking later on, and a lot of this work that he put into mathematics laid a lot of the groundwork for European advances later on in mathematics in order to actually figure out the things we need to figure out for calculus. So from Greece to the 15th century Islamic and Indian contributions, we seeing a lot of people using ideas of calculus but not actually understanding the fundamentals of, or like putting together all the pieces required to actually look at more of our fundamental theorems of calculus, and uh, a lot of them using geometry and other methods to find solutions, but not really concrete equations or other methods to actually put these into bigger context, I suppose you could say. So that brings us to the early modern period in the Renaissance, so about between the 16th and 17th century, when early Europeans were, after all the Dark Ages in Europe, and about 15th century, 14th century, when the Renaissance kicked off, there was a huge explosion of mathematical and artistic and religious ideas that were growing throughout Europe and throughout the rest of the world. And this is when we start seeing people begin to think about and incorporate a lot of these ideas of mathematics, using it to help us advance our civilizations. During this time, there was more advanced uses of geometry and using tangent methods, so finding tangent lines on graphs in order to solve different problems or equations, but not really yet getting into the actual calculus. And a lot of this work here foreshadows many of the ideas of later calculus in the 17th century. And then from a lot of the ideas that were built up in the early modern period, we finally get to Isaac Newton and Gottfried Wilhelm Leibniz in the 1660s and 1680s, when Isaac Newton and Leibniz independently discovered the theorems of calculus. And so Newton's ideas invented like he called it Flexion's form of calculus, and that it's a way to think about physics and how calculus works with gravity and motion. And then Leibniz independently developed calculus and created a lot of the modern notations. So our ideas of f and d dx in order to actually put these calculus ideas into terms we can put onto paper. And during this time is also a big dispute about who invented calculus first, but it's pretty widely considered that they both independently thought about this idea in creative ways separately of each other in a very close amount of time. So whoever invented first didn't really matter. So during this time, we are finally seeing the ideas of finding derivatives. So uh, using the idea of derivatives and finding the changes of a graph and applying the ideas of finding the area under a graph within this derivative. So actually trying to find what these areas are, kind of accomplishing two separate things at once is what we're trying to accomplish in this our end goal. And we want to do this with a high degree of accuracy because especially when working with curving graphs, we can't find these curves exactly without the use of calculus. So the calculus that we're going to be using helps us find accurate areas based off of the graphs we have. So now that we've gone over some of the kind of basic history of calculus and how it's developed and changed over known history, I'd like to go ahead and show you how to actually integrate and evaluate some calculus problems using USUB. So USUB was developed with the ideas of Leibniz and Newton, and used a lot of their thinkings in order to actually solve these problems. So USUB is a method we use to solve and integrate various calculus problems, and it's still used today for a lot of the teaching and a lot of the more basic problems in calculus. So one of the problems I'll start us off with is integrating 4x x squared plus 5 3 to the third power dx. So on basic, looking at this problem, we're trying to integrate 4x times x squared plus 5 to the third power. And an integration for right now is we're kind of just trying to find the antiderivative of whatever this equation is. Our methods of doing so are right now difficult to do just based off of looking at it. We can't use our principles to integrate between these two very easily, or anything that's inside of the parentheses here, or trying to handle with this exponent. There's a lot of different there's a lot of different complications to this that'll make actually finding the antiderivative of this equation fairly difficult. But one of the easiest steps we can start off with is this USUB method. So USUB is just trying to find a substitution, which is going to be we're going to call U, and then inputting that substitution into our equation, and that'll help us find our answers. So first we have to find a substitution for U. So it's usually easiest if you find something within parentheses or within some sort of function, or within the function that's within a parentheses or what have you. And if there's multiple things within parentheses, you want to usually use the highest exponent thing. So right now, using this x squared plus 5, which is within the parentheses, is going to help us easiest. So what we're kind of doing is a chain rule of sorts in order to solve this integral, which is why we're using the inside of the parentheses. So our u is going to equal x squared plus 5. And we need to put this into terms into this equation itself. So we have to actually get rid of dx as well. So an easy way to do that is to take du over dx and then solve for dx in our equations. We're going to set du over dx equal to the derivative of x squared plus 5, so that's 2x. And then we're going to want to solve for dx. So it would be du over 2x equals dx. And so this du over dx, we're going to replace our dx with that, so du over 2x. And then the inside, since we've already defined x squared plus 5 as u, we'll just replace this with u. Now we'll just take a look at the equation. So du over 2x, and then we have 4x. We can cancel those out and put them on the outside of the function. So we get rid of x. So 4x divided by 2x is 2, but since it's a constant, we just put it outside of the function. So we have 2 integral of u cubed du. And since we have a much simpler function within the integral, it's just u over 3, we can easily find the antiderivative of u over 3. And so the antiderivative of u over 3 is u to the 4th power over 4. And we still have this 2 here, so we're just going to multiply our equation by 2. 2 u to the 4th power over 4, and we just add a plus c because translate it onto a graph anywhere based off of how this antiderivative works. But now with this last equation, we have u here, and we don't want u anymore. We want to have x. So for this, we're going to go ahead and start off with simplifying the 2u over 4. So 1/2 u to the 4th plus c, and then we'll just input our x squared plus 5 back into u. So it'll be half x squared plus 5 to the 4th power plus c. And then that will be our final integral. So we'll do another one. This one will be using some trigonometric functions. So we'll go ahead and do the integral 8 cosine 4x dx. So similar to the last one, we want to try and find something that's within parentheses or within some sort of other notation. So we'll do 4x inside of cosine, so u to the 4x. And we want to find du, take the derivative of 4x, which is 4. We set that equal to dx, so that'll equal du over 4 equals dx. So now that we have our du, we'll take the equation and input u and du into the equation. So cosine u du over 4. And we can simplify, so get rid of the 4 under du by dividing it with 8, so that'll equal 2. And since it's a constant, we'll put it on the outside of the equation. Then we have cosine u du. And from here, we just find the antiderivative of cosine, so sine u. We still have the 2, so we'll put that back on the end. And we don't need the du anymore, but we'll need to put that constant of c. And all we have to do is put back in our x into u, since there's nothing else we can do. And then that'll equal 2 sine 4x plus c. And that's going to be our final integrated equation. So now we're going to find methods of solving definite integrals. So for our definite integral, we're going to go ahead and put integral 2 to 0, 2x, x squared plus 4 squared dx. So the difference between this problem and the last one is, of course, we have these new boundaries for us to actually find the answers to. And this is now that we actually have where we're trying to look at the equation, we're going to be able to very easily solve this equation now that we have our limits to it. So like before, we're going to find something within some sort of notation and try to find a u sub for it. So in this case, we're going to use x squared plus 4. So u equals x squared plus 4. We're going to find du for that. And in this case, derivative of x squared plus 4 is 2x. So here we'll just solve it to dx. So du over 2x equals dx. We have to change the equation so that it's integrating properly to our new u sub. So we're going to have to change this 2 and 0 here. And the way we're going to do that is take our original sub, our u sub, so x squared plus 4, and we're going to actually put in 2 and 0 and find the answers to those. So 0 squared plus 4, because we're putting in 2 and 0 into our x here. And that's going to equal 4. And we'll do the same for 2. So 2 squared plus 4 equals 8. So now we're going to be integrating from 4 to 8. So our equation's going to look like this. 8, 4. And then start 2x. Replace the inside with u squared du over 2x. So this one's a lot simpler for getting rid of the du over our 2x. So we can just cancel those out. And all we're left is integrate 4 to 8 u squared du. So we'll just find the antiderivative of u squared, u3 over 3, or u to the third over 3. And we still have now that we have a definite integral, we have to find from 8 to 4 of this equation itself. So since now we're just have to find the answer to this equation. So it's going to be 8 cubed over 3 minus 4 cubed over 3. And if we solve that, it's going to come out to 512 over 3 minus 64 over 3. And that is going to come out to 448 over 3. So finding this definite integral, going from actually having bounds to our integral, we were able to get an actual answer and solve for it using the u sub method. So the final answer is going to be 448 over 3. That's the ease and simplicity of being able to use u sub in order to solve a lot of these calculus equations. Is now something that seems very daunting and very difficult to do using normal methods or trying to find antiderivatives and trying to solve for potentially hundreds of different equations going from 0 to 2, or even higher, from 0 to a million, or whatever it is. We can actually find a lot easier using this method and doing a lot less work than we would possibly need to have to do. So I'll go ahead and do one more u sub of a definite integral. So integrate 4 to 0, 4x square root 16 minus x squared dx. So this time we're using a square root, which can can definitely complicate things, especially since we need to start paying attention more to our exponents and whatnot, and our rules of our product rules and other antiderivative rules. Just like our other ones, we're going to try to be looking at something within notation. So we're going to be integrating we're going to u sub for 16 minus x squared. And we're going to find dx. So the derivative of 16 minus x squared is negative 2x. And we'll just solve for dx. And now that we have our du over dx, our du's figured out, we'll also do the changing our integration. So remember, we're just putting in 0 and 4 into our x for the u we decided on. So it's 16 minus 0 squared, which equals 16. And then 16 minus 4 squared, which equals 0. So when we're doing this, making sure we're paying attention, because now 16 is on the bottom of our integral. So 16 and 0 is down here. Make sure you put them back into the correct locations when we're done with them. We'll go ahead and plug in our u's. 4x square root u over du over negative 2x. That's going to come out to, after we solve for this, so negative 2 over, negative 2 integral of u 1/2. This will change the notation, is going to make it easier when we start doing the antiderivative methods. And now all we need to do is find the antiderivative of u to the 1/2 power. So that's going to be u to the 3 over 2 2u over 3. And we still have the negative 2, so add that is going to come out to negative 4u 3 over 2 to the 0 into 16. So now we need to go do this integral from 16 to 0. So just like before, we're going to be plugging those numbers into our equation and solving. Negative 4, 0, 3 over 2 over 3 minus negative 4, 16, 3 over 2, 3. And when we solve for this, we're going to end up with 256 over 3 as our final answer. So using u sub, we now can see how we can integrate. And from integrations and from learning how to actually integrate and using the methods of u sub, we can actually find the answers to definite integrals. So integrals with bounds to them, and finding the answers to them using much simpler methods than trying to do potentially hundreds of equations all at once. Because like with this one, for example, if we were to find 0 to 16 through normal methods, we would have to do the equation over 16, 17 times in order to actually find this answer. But using u sub, we can both find the antiderivatives and then find the summations of a lot of these equations very easily. And so that is the conclusion of my brief history of calculus, and then showing you how to do some u sub on different calculus problems. Thank you for watching, and I hope you have a great day.